Lecture 4, Predicting Wine Quality. This is the second part and the last part of recording of this lecture. Multiple linear regression. Here we assume that we have k independent variables and also n observations. So let's have an example here. Okay, the observation number, let's say 1, 2, up to I, okay? And the y variable as the dependent variable, so we'll have y1, y2, yi up to yn. And here we have the independent variables x1, x2, okay, up to xk, okay. So here it will be x1 for observation 1, x2 for observation number 1, up to xk for observation 1, okay. And for I will have, for example, x1 for observation I, x2 for observation I, up to xk for observation R, and so on, okay. So here we want to have a prediction for the outcome, the dependence variable for the y, by having a multiple linear regression. Why we call it as multiple? Because here we have multiple independent variables. If we have just one independent variable, it will be a single variable linear regression, but here we have multiple ones, so it is called multiple linear regression, okay. We usually show the prediction by y hat, so y hat 1 up to y hat I, so and so on, okay. And yi is obtained by this linear equation, okay. As you see here, beta 0, we have an intercept, and then the slopes or the coefficients beta 1, beta 2. So beta 0, beta 1 up to beta k are the coefficients, and we have this linear function to predict observation, to predict the dependent variable of observation I, okay. So here, in order to obtain the values of the coefficients, in order to build the linear function, we will obtain the sum of squared errors, okay. It will be sum over I going from 1 to n over n observations, and the true value of the dependent variable yi minus the prediction one, y hat I to the power of 2, okay. So we will minimize this sum in order to obtain the value of coefficients beta 0, beta 1 up to beta k, okay. So this is how we obtain a multiple linear regression model, okay. After building a linear regression model, we need to evaluate the quality of the model. So the first step here will be evaluating the significance of the independent variables. When we have k independent variables, it doesn't mean that we need to have all k variables in our model. Maybe some of them uh, are not impacting on the change of the dependent variable. So a coefficient is considered significant if it is significantly different from 0 based on the data. So if we see some of the coefficients are so close to 0, that means those variables, those independent variables, are not significant enough. So we can remove them from our model, right? So here we have three measures to evaluate the significance of the independent variables. The first one is a standard error. So what's the definition of this measure? A standard error is a measure of how much the true coefficient is likely to vary from the estimate value given the data. So as you see here, the smaller standard error, the better situation, right? The t value, this is the estimated coefficient divided by the standard error. So we divide the estimated coefficient, the value of the coefficient, by its standard error. So here, a large absolute value would be the better, right? Because the t could be negative or positive depending on the sign of the coefficient. So here, this is why we say the absolute value here. Okay, so the large absolute value will show that that variable is significant. Okay, so because the small standard, I mean a large absolute value means having a small standard error relative to the coefficient estimate, right? And the third measure here would be p-value. P-value would be the probability that the coefficient is actually zero given the data. So again, higher probability, higher p-value will be insignificant variable, right? So the less p-value will show the significant variables, okay? Let's see why we need to remove insignificant independent variables. The first issue we may have here is overfitting. Overfitting occurs when we have too many independent variables compared to the number of data observations. If we have a very large set of observations, I mean the number of data observations is much more than the number of independent variables, then in that case, we shouldn't be worried about the issue of overfitting. Even if we don't remove the insignificant independent variables, again, we won't have the issue of overfitting. So the overfitting will occur, most likely, will occur in the case that we have too many independent variables compared to the number of data observations. So this is why we need to, it's better to remove the insignificant independent variables. Another reason for doing this is having a simple and interpretable model. So when we have fewer independent variables, so our ability for interpret the model will increase. At the same time, we will have a simple model, and that's much better, right? When we need to remove insignificant variables, and if we have multiple insignificant variables, we should do this one at a time, because we may have the effect of multicollinearity. When, for example, let's say if we have two independent variables that are highly correlated, then this correlation between these two independent variables will influence on the significance of these variables, and we may see these two variables are insignificant. But when we remove one of them, then the other one may be significant, because when both are present in the model, both are presenting the same thing, and this will make them to be insignificant, okay? But when we remove one of them, the other one may be discovered that, oh, it is significant. So this is why we need to remove the insignificant variables one at a time, okay? So you can actually remove the least significant one first, right? And also you can also apply your judgment based on your intuition and experience that you have in that area. That would be also a good idea to consider which variable should be removed first, okay? R square. R square is another important performance measure to evaluate our regression model. Okay, so R square is obtained based on a comparison between the built linear regression model and a baseline model. So what's a baseline model? The baseline model here does not use any variables. So regardless of the independent variables, the baseline model will predict same outcome for all observations, right? So here, so what could be a baseline model then? So here we have uh, the observation. So we have y1, y2 up to yn as the outcome, right? And also we have the independent variables. You remember that, right? So here we ignore all the independent variables and we just take an average over the outcomes, the dependent variable. Just sum over I going from 1 to n yi divided by n, so y bar. So here the y bar will be our baseline model. So we predict same value for all observations. So y bar, the mean of the outcomes, will be our baseline model. So here the red one, as you see here, the red line is our baseline model, okay? Average of the outcomes. And the green one is our linear regression model. So we will see how the linear regression is performing against the baseline model. And based on that, we'll obtain R square, okay? So how we will interpret the value of R square. So here we can say the R square value will show what proportion of the total variation of the outcome is accounted for by the independent variables. Okay, so if we have higher value, a high value for R square, that means the independent variables have great impact, have significant impact on the change of the outcome. But if we have a small value for R square, that means it is so close to the baseline, right? I mean, the baseline is a good prediction model here, and that shows that, okay, independent variables have almost no impact on the changes of dependent variable or the outcome, okay? And another interpretation would be the value added of the linear regression model has over a baseline model, okay? And one of the advantages of R square is being unitless. So this measure is unitless, and its value would be between 0 and 1. So R square, if R square equals 0, zero value for R square will show the worst case. That means there is no difference, absolute no difference between the linear regression model and the baseline model. So there is no value added here. And the best case would be R square equals to 1. In that case, it shows, the regression model is working much better than the baseline model. Okay, so this is the best case. Okay. So in general, a higher R square value implies a better regression model, right? But it depends. It depends to the application area. We should consider, we should take into account the application area beside the value of R square. We shouldn't just consider just the value of R square and say, okay, this model is good or it's not. No, that's not the case. We should see what's the application area. For example, if we are applying a regression model to a very hard and complex problem like predicting stock prices. So we all know that predicting stock prices is not a simple job. It's very complex, right? In that case, if we have a linear regression model and the R square is actually low, but maybe that model is good enough in that application. Or if we have a regression model for a very simple problem like predicting revenue of a product based on the items sold. So we know that this problem is so easy and simple, and maybe there is no value in having a regression model for this prediction. But if we do have a linear regression model for this, then we will most likely we will have a very high R square, right? So yeah, as you see here, it depends. It depends to the application area. So evaluate the use of the model in practice along with R square. So yeah, you should consider the application area along with the value of R square. Okay. So here we show how the R square is calculated. So the formula for R square is this. Okay. So here we show the numerator here in the fraction by SSE and the denominator by SST. So SSE is the sum of squared error, and as you see here, it's considering the y hat I. Y hat I is the prediction obtained by the regression model, right? So here we are actually taking the sum of squared error between the true value of the outcome and the predicted one with the regression model. So this is the performance measure of the regression model. SST is for the baseline model. So as you see here, for the baseline model, let me show here. Yeah, the baseline model here, we assume y bar. So the y bar, the average over y, is our prediction. So same value for all observations. So this, the denominator, actually this is the performance measure. I mean, the sum of squared errors for the baseline. So this is for the baseline model, and this is for the regression model, right? Regression model, okay? So now 1 minus SSE over SST. So here, if SSE becomes 0, if SSE becomes 0, I mean, we have a linear regression model that works perfect and there is no error, and it perfectly estimates, I mean, predicts all outcomes by inputting the independent variables. Okay, in that case, R square becomes 1, right? So this is why we say the value of 1 for the R square is the best case. And what if SSE is not working good, is not working better than baseline, right? In that case, SSE will be equal to SST, right? In that case, we'll have R squared of 1 minus 0, sorry, 1 minus 1 or 0, right? And so when we have the value of 0 for R squared, that means the regression model is not working better than the baseline model. So there's no difference between the baseline and the regression model. So that's the worst case. So based on this, we see that the higher value for R squared will show a better model. So in this example, for example, we have the R square of 0.42. Okay. Adjusted R square. Some softwares like R show adjusted R square as well. So what's adjusted R square? It's a modified version of R square by including the number of independent variables. So here is the formula. As see here, we are considering k as the number of independent variables in calculating adjusted R square. So adjusted R square will always be lower than R square if we have more than one independent variable, okay? And this will actually, since it's always lower than R square, so we can say it's more precise than R square, so we can actually consider this and it is more reliable, okay? Refining the model and final step. After building a linear regression model, as we discussed, we need to see if there are any insignificant independent variables. So if there are, then we will remove those insignificant variables one at a time, okay? So yeah, we should check for the significance and also multicollinearity. So this is why we remove the insignificant variables one at a time. And then we need to make predictions. Okay, so here we should have at least two sets of data. One set would be considered as training data set, and we will build our regression model based on the training data set. And then we will apply the regression model on the test set, the test data set, to see how it performs over the test set. So if we see a very good performance on the training set, but not a good performance on the unseen data or the test set, then we might have the overfitting issue here. Okay, so if we have just one data set, then we need to segment our data set to two segments, one as training data set and the other one as test set. And usually we check the performance of our model on the test set, not just on the training set. Okay. So by learning the steps of building a linear regression model and refining it and evaluating the performance of the linear regression model, now we want to build a linear regression model for our data set, which is about the quality of wines, and we'll do this using R. So we'll have this in separate recording. Okay. The results here that we have for the Ashland filters regression model compared to the experts' prediction. So in 1991, the Parker, as an expert for tasting the wine quality, predicted that the wine of 1986 would be a very good one. But in the same year, Ashland filter predicted by the regression model that 1986 would be a mediocre, but 1989, I mean the wine that has been produced in 1989 will be the wine of the century, and 1990 will be even better. Okay, in 2003, after a while, after about 12 years, right? Yeah, after 12 years in 2003, market discovered that 1989 and 1990 are outstanding. And 1989 sold for more than twice the price of 1986, and 1990 sold for even higher prices. So you see here how the performance of the regression model compared to the Parker's prediction. Okay, and in 2003, Ashland filter predicted the one produced in 2000 and 2003 in the same year would be great. Okay, and Parker has stated that the wine produced at 2000 is the greatest vintage has ever produced. Okay, so yeah, by this results we see that the built linear regression model by Ashland filter for predicting the wine quality works perfect, works perfect and has better performance than the experts. So to wrap up here, we see the analytics edge here. Having a linear regression model with only a few variables can predict wine prices well, and in many cases, it outperforms the wine experts' opinions. So previously, obtaining the quality of wine was a qualitative problem. Actually, it needed to be tasted, right, by the experts. But now we have a quantitative approach for that problem, and we see how it performs. So this is the analytics edge here. Okay, thank you.